So here's a couple things, just some concepts. So information is one. Dishonesty is another one, and then money is one other thing I want to talk about a little bit. Actually, let's start with money first. And one thing that I hadn't really thought about much until a few years ago is the fact that money actually is purely a concept. I mean, sure, it has a lot of physical manifestations, but I'm just going to say money is maybe merely is not a word, but money is a concept with a myriad of physical manifestations works. Well, it's physical, and it can also be non-physical. Like you can pay for an idea, you can pay for someone's patent. And one good example of that is I'm going to see if I can find it. There was some very telling. I'm just going to Google around for one quick second. Money as a concept, ancient, large stones. Oh, this might be it. Yeah. Here we go. Yeah. So here it is. For centuries, the Yap Islanders have used huge megalithic crystal discs, so these stones, they got a hole in the middle, as their money. Shaped like gigantic wheels and carved from single blocks of calcite crystal, the stone money is called Ra. Largest yet discovered, 12 feet in diameter. Special reserve. So they're just like Fort Knox sitting there, some large et cetera. And it's just, so it's the physical manifestation of the idea, just like a dollar bill is our physical manifestation. But the most telling story, let me see here. Okay, this is it. According to a local legend, one of the most valuable Ra stones was lost at sea in a great storm and never made it to Yap. The huge crystal now lies at the bottom of the Pacific. We assume, I've never seen a photo of it, but here's the legend. 100 miles short of its destination, islanders agreed that this particular Ra stone was now of great value, even if they couldn't set eyes on it. So they sort of just agreed, yes, that money is in the bank. It does exist, and it's no different from the money you might make in your own bank, because it's just sitting there on a computer. I mean, it's not imaginary in that it actually is a set of ones and zeros, but on the other hand, it is imaginary in that we've just sort of agreed that it has value, even though we can't see it. So that's and I'll just put this little link in there. It's a concept. And it has to be, and the Ra, the Ray, or however you pronounce it, is just one physical manifestation for that particular society. And so here's how people make money by having information. and exploiting others' lack of information.
Lawyers.
What's that?
Lawyers do it all the time.
Oh, absolutely, yeah. Yeah, so, and this is where dishonesty comes into play as well. And so there's a couple of things. I don't have the article here in front of me. I'm gonna type it so I remember to find it. But it's the New York Times Magazine article on millisecond trading. So stocks are just another type of money, right? And theoretically, the stock represents some physical manifestation. That's the company. So the stock is just yet one more layer of money, if you will. And what this particular maybe I can find him. Brad RBC Canada microsecond trading New York. I used to.
I don't have TV anymore, but when I did, there was a story on this guy.
Yeah.
60 Minutes was really good.
Yeah. This is him. I didn't know. Okay, so Brad Katsuyama. I'm gonna pop his name right in there. Was just entry-level banker, 20-something years old, working for the Royal Bank of Canada, and was sent off to New York City to try to make some more money for his bank, right? So he went off to try to partner, trade, whatever banks do, so that the Royal Bank of Canada could actually have a bigger slice of the pie, whatever that means. And so what they noticed is that a lot of banks were trading stocks, owning companies, doing investment banking. And what he also noticed is that when he was trying to do his own trades, he'd have a customer come in and say, hey, can you buy such and such for me? All of the, not all, but a very large fraction of the trades that he thought were going to be the most lucrative would sell out just before he was pushing the button. In a similar way, you might be there trying to buy your plane ticket online. Oh, I want to get to Hawaii in December, but somebody else buys it, right? Because he's out there doing the same thing. Well, as it turned out, he discovered that there were, in fact, the closer and closer you got to the main server, that was actually the buck stops here, the official record of the stock exchange. There were other traders sitting between him and that exchange, stealing from him and hiding the fact that they were stealing because they had faster computers. And it would sort of happen so quickly, within 5 or 10 microseconds, which on a computer is forever. I mean, this bad boy is running at gigahertz, right? It's running a billion bit flips a second. So 1,000 a second, you can do 1,000,000 trades in a single microsecond if it's 1 bit per trade. So this is where the dishonesty part comes in. And so if we come back up to our own little matrix, so theoretically, we in energy finance are going to educate ourselves sufficiently so that we know what these numbers are. We do the research, and so that we can prosper on someone else's ignorance. I think a lot of times that's kind of what it comes, because, and in fact, not to be cynical about it, but a a bicycle mechanic is going to prosper on someone else's ignorance. They're going to make money because the bicycle owner is ignorant of how to fix their bicycle. The TV repairman is going to prosper on someone else's ignorance because they don't know how to fix their TV. Prosperity. So I want to throw that. I want to throw that one in there. Ignorance. There's another one. There's another one you can see prosper. Prospering on lack of time. Prospering on someone else's lack of time. And this could be, so here's an example. Bike mechanic. Lack of time. This is going to be example, lawn service. So someone's going to come out and mow your lawn, not because you don't know how to mow your lawn, because you don't have time to mow your lawn. Neurosurgeon. I would do my own neurosurgery, but I don't know how. You wouldn't put the neurosurgery in the same bracket as a lack of time. Well, no. Well, it could be that too. I didn't have time to go to 10 years of med school to learn how to be a neurosurgeon. Prospering on ignorance. I'm just going to say, lack of information. I should write it this way, prospering on someone else's. And it's the same thing up here, is if we're going to go to the trouble of making our own little PV gadgets that are then grid tied somehow, or microgrid on our own little microgrid tied somehow, we'll prosper in the same way because not everyone knows how to solder or how to fabricate, et cetera. So we have to abide by the same model. But here's what we can do is we can actually educate, so we can provide our own information to the consumer as to like what they're paying now to what they could be paying. So we're going to share that little bit of information with them. So we will share the bad news of business as usual. Right, so we're going to have to tell the consumer, here's the bad news of the business as usual. Your power bill is going to go up, or planet's going to be destroyed, et cetera, whatever, however you want to sell that. Okay. And here's what I wanted to, another thing I wanted to pull out on that. Papers. This has not been published, and I don't think. Tell me if you've already seen this paper yet. I'm still working on. Have you guys seen this yet? Have you seen this one, Gary? Okay. So this is kind of bigger picture stuff that I've been trying to work on, and it ties in. Well, yeah. Well, that's kind of that's why professors are called, professors. Yeah. So here's the deal, though. You guys know what anthropogenic is, right? Human caused. Entropy is energy per Kelvin. You know what acceleration is. It means that the pace is quickening. Shannon information, I'll show you here in a little bit too. And then socioeconomics is distribution of wealth. You know, like why some people have more money than others. Okay. So let me, so entropy, I'll dig into it a little bit here. Here's information, and there's socioeconomics. So what I said, this is done via quantitative exploration of entropy generation at scales ranging from the nanoscopic to the cosmic. A working quantitative relationship between entropy and information in several systems is then explored in detail. And then exploitation by selfish, dishonest systems of contingencies implicit in socioeconomics. Okay, what the heck does that mean? Well, a selfish, dishonest system is someone that's just serving themselves, right? Like kind of a fascist or a dictator, or I don't know, name somebody else who that's all they're doing. They're lying and only care about themselves. So the opposite person that what Adam was talking about in his initial goals. Now contingencies, this just means, this could mean randomness. So for example, what's a good contingency in socioeconomics? You know, like a Walmart may or may not come to town. So when the Walmart comes into town, all of the small business owners downtown go out of business, and then the ice cream shop goes out of business, and then on and on. Some urban blight, et cetera, et cetera. So it could be just, you know, this contingency, this one little random event that causes this sort of domino effect that the other selfish, dishonest systems can then take advantage of. Okay, and I tried to be as quantitative as possible by actually saying what entropy is and what information is. So let me just do that now, and then I think we'll have a bigger picture on where our little plan sits in this whole scheme. Okay, so by now you guys know what joules are. You certainly know what seconds are, and you certainly know what Kelvin is. It's just temperature. So those are the units of entropy generation. So entropy is just joules per Kelvin. But if you then if you take it on a per second basis, it's the same as like looking at, so if you divide energy by time, you get power. So you can think of this as sort of like entropic power, the rate at which disorder is being generated in any system. And I'm going to hop way ahead really quick, because at the very end, this is a super easy, super brief.
So is entropy always considered destructive?
Entropy is not always considered destructive.
You know, like, is it negative?
It's not destructive, but what it is, in fact, Richard Feynman gives a pretty good example of what entropy is. And so you just swam in the ocean, you come up to dry off, and you're with several other people, and you've got one dry towel. So the first person dries off, and now you're less entropic because you're drier, your body's more comfortable. But all of the disorder, your dead skin, the leech that was stuck to you, the sand, the salt water, that's now all in the towel, right? And then the next person comes by, and like, oh, sorry, man, here's the towel. You don't really want the towel, but okay, I can still scrape some of the crud off and the sand, and then the next guy, maybe he's able to clean it. Eventually, the poor towel is so dang messy that the 10th guy is just going to be worse off using it. So it's not necessarily destructive. It's taking things to a state where nobody wins. And so here's the deal. And this is like straight out of textbook. I mean, if you want to argue with this, you're going to have to overthrow Newton, Galileo, Carnot, all of them. This is pretty straightforward. So two planets of equal size and mass, but two different temperatures. The one's hotter than the other ones. We can quantitatively demonstrate the non-conservative nature of the second law. So non-conservative means that, and sorry to jump around so much, but I can bring this right back to that Nash paper. Let me bring it right back to the Nash paper. In a conservative system, everything is always going to keep adding up to zero. You'll never get outside that boundary. 0, 0, 0 every single time. I give you $1, you give me $1 back. Dollar, dollar, dollar. There's no friction in the system, and it always ends up being 0. So, non-conservative, something is going to become larger, no matter what. And what that thing is the universe is going to become more entropic. So planet A is at 298 Kelvin. I think that's about room temperature. Planet B is 283 Kelvin. So, what are we looking at? 15 Kelvin cooler. So let's say 25 Fahrenheit. So it's the difference between 90 and 65 degrees or so. It says that spontaneous energy will occur from planet A to planet B. The hotter one, and they're both radiating. Anything that's above 0 Kelvin is radiating. But there's going to be a net effect. So spontaneous energy transfer from A to B. Say, for example, that a radiant energy transfer occurs at a rate of 2330 watts per kilogram. Now, that's a pretty beefy rate of transfer. In our own bodies, let's just say you weigh about 100 kilograms and you're running about 100 watts, your own energy rate is only 1 watt per kilogram. But if you look at like a combustion engine, it's going to be maybe 100 times more powerful. So you might have a combustion engine of 100. But this is, and I don't know if that number is really the best, because something that's that cool probably isn't doing nuclear fusion, but that's basically what that is. It's kind of a nuclear fusion. You got 2 kilowatts coming out of your cup of coffee is what we're looking at. And there's 2 cup, like you got two houses worth of power coming out of one kilogram of matter. So, what is the rate of change in entropy of planet A? So guys, if you remember, the dot just means the rate of change. So the letter S itself is entropy, and then the dot is the rate of change. So if you were thinking of S as energy, you put the dot over, it would be power. But instead, the S is entropy, you put the dot over, it's the entropy generation rate. So, there's T in the bottom for temperature. You just plug the planet's temperature into the bottom. And then the power rate, that's just a Q, and it's just thermal. Q is typically thermal energy. Put the dot over the top. And so it's giving off this negative 2330 watts per kilogram. Now, where is it going? Well, it's hitting planet B.
I don't know how you got the negative, but I won't ever understand that. You can explain that to me forever.
No, yeah, here. So I have a phone. I have a phone, and my phone count right now is 1, and yours say 0. And I gave you my phone, and so 1 minus 1 is 0. I had to put a negative there, and so that's where the negative comes from. I no longer have, I had 1 minus 1 equals 0. You had 0, now you have 1, so that's the plus. My negative has to be your positive, because I just gave you my phone.
I said, I'll never understand. I would have did it, I could have got the answer, but I would have, instead of adding them together, I would have subtracted it in the bottom.
Oh, yeah.
It would have been
It is
the
confusing.
exact same thing, but it would have been subtracted, but.
But how do you add it? How do you add a negative? Is that the
Well,
concept?
how do you subtract A from B? Because you'd have a negative number there at the end.
Oh, I see. We'll get to that. It's good. I'm with you. But I think you can see in the first equation, though, why it's negative. 'Cause I just lost it. I mean, it's no different from writing a check in your checkbook. You write a check in your checkbook, you put a minus sign. If you write a $100 check, you got to put a minus sign. You can't put a plus sign. Because your balance just went down. So planet A is giving up entropy at a rate of 8 watts per kilogram per Kelvin. Now, where's it going? Some of it goes to planet B, and whatever A is losing, B is gaining. Now, here's the difference, and what's different about it is since planet B is cooler, it's the denominator is smaller, so the overall magnitude of the number is greater. 8.2 is greater than 8.0. So when at the end of the day, you go to add up all of the entropy changes of all of the planets in the universe, and this is why you have to add them together. You're like, how much did your entropy change? Well, it could be that some of them are negative, and in fact, planet A's entropy is negative 8.0, and as it turns out, planet B's is positive at positive 8.2. The positive number has a greater absolute value than the negative number, so the total entropy went up for that two-planet system. And it's happening everywhere as stars radiate their entropy out to cooler planets. So this is a example. You can't argue. I mean, you could.
Well, the only thing I like I said, still am kind of iffy on the negative, but
Sure.
if you get down to your .171, where's the equilibrium balance in that? Because at some point, this planet
Yeah.
B is going to heat up to the point to where planet A is cooling.
Yes.
And releasing, there's going to be an equilibrium point in the middle to where it doesn't.
Perfect. And you're exactly right. It'll be at equilibrium when their temperatures are the same. I'm really glad you asked that. So as soon as planet B has a temperature of 289, then they will be in entropic thermodynamic equilibrium.
So
Does that make sense? I mean, it's the same thing like you're snuggling your girlfriend, right? I mean, if you're warmer, she's colder, eventually you'll become the same temperature.
if your planet's giving off 289 Kelvin or at 8.62 Kelvin, wouldn't that be subtracting it from that? Or you're just constantly generating 289 Kelvin?
Yeah, it's constantly generating. Yeah, what it's doing, and this is the subtlety of entropy, is it's not energy, it's energy per Kelvin, and the energy is coming from gravity. Gravity is squishing the. It even happens on that. Well, we radiate. The Earth radiates at 60 milliwatts per square meter. We were a hot ball squished together, and all of the fact that our core is still hot and somewhat liquid, is just as a result of all those atoms squishing together. And we radiate, nothing near the sun, but we're constantly at our wimpy little 60 milliwatts per square meter, but that's a number, that's the average number. Okay, so what I'm showing here is that entropy is not conserved. Now, big leap. I'm going to pop this out here. Maybe I'll pop it right up here. Entropy is not conserved. Neither is money. Sorry. But think about it. So the bank's going to give you a loan, and how much are you going to pay them back? You're going to pay them back more because they're banking on your time being worth something. So the bank has made money out of thin air, and that thin air is your time, more or less. So same thing. We just saw in this example, entropy just keeps getting bigger and bigger, up and up. Same thing with money too. Is the stock market really worth what it is? Over 17,000 now, it's at 16. Well, no, it's a big fake imaginary thing too. But as long as everyone's sort of agreeing that it's real, then it is, and we do. Okay. Now, there's your entropy, and hopefully at least, whether you understand it or not, those are the numbers. That's what it is. Now, let's look at, and also, by the way, entropy is as real as mass. It's as real as time. It's as real as space. If you want to argue about their reality, it's fine, but it's as real as physics. Okay, now, information is the other side of the coin that I want to.
Just passed it.
Yeah, I know, it's all over the place though. I want to show you the definition of information. Then I'll get to that little example. Okay. So information is this. This is what Claude Shannon, he didn't win the Nobel Prize, but he won some other giant engineering prize for coming up with this little equation right here. And it's not unlike the Nash paper that we just looked at. But here's what it is. This is the probability of something happening. And again, flip of a coin, forgetting your wallet in the morning, whatever. Assign some probability. Either it's going to happen or it's not. But if it's never going to happen, it's a 0. If it always happens, it's a 1. And then if you multiply that by the natural log, God, maybe I've got a typo here. There's different ways to take a log. You can take log base 10. You can take log base e. You can take log base 2. You can take log to whatever. But if you take the log of a number between 0 and 1, and let's just do it. Let's just take the natural log of 0.5. I know that number is going to be negative. It's always negative between, because anything to, let's just do it this way, equals natural log of 1, 0, then here goes natural log of 5. It's positive. So the log crosses the 0 at 1. So anything between 0 and 1 is negative, 1 is 0, and anything greater than 1 is positive. So that's why this little negative sign is here, because this probability, the log of this probability is always negative. And the probability itself is always positive. Anytime you multiply a positive number by a negative number, you get a negative number. So this little chunk is always negative. You put a negative sign in front of it, and it's always positive. Can't argue with that either. So that is the definition of information. And let me show you an example. And you can do it for anything. Horse racing, stock trading, who's going to bomb who next, Israelis or Palestinians, whatever. Anything has some probability. Me blurting into some Tourette's at the moment could happen. Hopefully not. Okay, so here's what ends up happening. So if you've got probability 1 versus probability 2, and they're mutually exclusive, heads or tails. I'm alive tomorrow or dead tomorrow. Forgot my car keys or I didn't forget my car keys. Whatever, one or the other is going to happen. Now, if it's 50-50, if you got a 50-50 chance of one of those occurring, for one event, that contains 1 bit of information. And you can think of it exactly. It's what we do all the time on our computers. It's one bit of information. Now, if it's going to happen twice, you're going to flip the coin today, and you're going to flip the coin again tomorrow. That now just contains 2 bits of information, and it's just linear like that. Now, here's what ends up happening. Let's look at a scenario where I'm glad I'm looking at this because I got a little typo. That should just be 1 instead of 100. So let's just assume those two zeros aren't there, but it's a 1. It doesn't matter. 100 divided by 0 is the same as 1 divided by 0. But if you've got it's going to happen. Everything's going to happen the same all the time. 100% chance. There's no information there whatsoever. If it rains today and it rains tomorrow and it rains the next day, and your buddy says, "Hey man, it's going to rain tomorrow," you're like, "Tell me something I don't know." So literally, there is no information in that statement. If you know it's going to happen, 0 information. And the reason is that if we come back in here and we take the equals the log of, takes the log of 1, but there's your 0 right there. That's how it turns out to be 0. So Claude Shannon came up with this and became very, very famous as a result. Now there are other scenarios somewhere in between where if it's very likely to happen, let's just say 99% to 1 of something happening, there's a little bit of information there. Like once in a while it doesn't rain, and once in a while the weatherman's right, and so you might say, okay, great, I'll throw you a bone there. There's 8% of information, whereas before, gosh, if you had no idea whatsoever, it's 50-50, and someone tells you exactly what's going to happen, you fix the horse race, you fix the boxing match, or however you want to look at it, then that's valuable information. Okay.
I suppose you tell them questioning the information. Let's say you don't have the information, or I don't have the information.
Yeah.
There's some point that you are giving off information, like radiating.
Yep.
To me, that the equilibrium point comes. Aha, I got that.
Oh, yeah.
Jesus moment.
Yeah.
Now I don't need that information.
Yep. So I did that just a little bit here. So let me show you the aha. So we know what entropy is, we know what information is, and now what I tried to do is just this. So, well, I shouldn't say everything's making information all the time. Some things don't, but your stock analyst, your bookie, your life coach, whoever it might happen to be, your computer is making information for you. And all of these physical systems are also generating entropy. So if we just divide those two, this one's measured in bits, this one's measured in joules per Kelvin, we can come up with another coefficient and say that any system can have its own little alpha. And I call it informational fitness. And what that means is that you're able to make a lot of valuable information, give people their aha moments without making much entropy. So big entropy producer, Hiroshima bomb. Big entropy producer, Hurricane Sandy. Big entropy producer, the next Ebola virus outbreak. But if I've got the information in hand, like, hey guys, look, I'm looking at my radar. Here comes the hurricane. Get the heck off the beach. Or hey guys, I've got this antivirus serum, or I just completed my study and it turns out, if you change your underwear once a day and wash it, you don't eat Ebola, whatever it happens to be. If I've got this information, I can prevent the entropy. So what I try to do, I did something with the Google car to say how much information it generates divided by how much entropy it's making, because any engine also makes entropy. I came down here, like a computer virus, like how much, with one little bit of, or not one, I don't mean bit literally, but with a small number of bits, you can make a whole lot of havoc. I even did like a little home energy monitoring example. So if you've got sensor data coming in, and all you need is to know the temperature or the light or whatever it happens to be goes through your computer, and then you can keep the house much more comfortable, and you're not driving out to go and buy the window AC fan, or you're not calling up the HVAC guy to come change your air, because you've got better information about what's happening in the environment, and you can just close a duct or a blind or something here. Okay, but then finally, the last thing I want to say on this is okay. I know I've got Lance Armstrong in here somewhere. Okay, so Lance Armstrong became very, very famous, made a lot of money because he was a fantastic liar.
Seriously.
Brilliant liar. and bullier. Same can kind of be said with Martha Stewart and her little insider trading thing that she was doing. She was caught for. I'm sure there's thousands of other people doing the same exact thing, but somebody just had it in for Martha and wanted to.
Bernard Madoff, that's who I was thinking of.
Bernie Madoff.
The Wolf of Wall Street, right at the end, it's like Bernard Madoff. That's who that was.
So I think he was living pretty large for a while, and doing so because he was just a fantastic, dishonest guy. Spitzer, right, with his prostitution ring, Clinton with all his, and in fact, when it comes right down to it, for gosh sakes, every single politician has to lie, because if you go back, let's go back to our little 50-50 table right here. This could be your Democrats and your Republicans. It could be your pro-lifers versus your pro-choicers. It could be whatever have you. Every single topic on which people decide, of course it's not 50-50. You can't say that 50% of the people are one and 50 or the other. But what you can appreciate, though, as a politician, is to know that every single person is going to fall into one of those camps. And how many votes do you have to stay in office? Regardless of your own values. And I think we kind of assume for the time being that the politician's main objective is probably just to get into office, to stay in office, their own values and ethics aside. So what they're going to have to do is lie well enough to both sides, so both sides think that they're on your side in as many topics as possible. So, and then I think like the other place you were going there, Gary, and you're dead on with this look at the information in the same way as the entropy. So it could be that, gosh, I just figured out this neat little thing. I'm going to go to Wikipedia and I'm going to go in and type in my little edit to this thing. This guy was my undergrad mentor at MIT, and I probably know a few things about him that aren't on this website, so I could go in and type it in, and then presumably as soon as it's on the Google, I've shared that, in the same way that hot planet is sort of spraying out its entropy. I'm spraying out my information, and then eventually, everybody knows it, right? Everyone's a Da Vinci, everyone's a Picasso, and we all kind of know, big deal. There's nothing new there. So it really is only information if it's, first of all, conveyed properly, but also understood. If I were standing up here trying to give this lecture in Chinese, there would be no information transfer because you wouldn't know what I'm talking about. I could sit here and think I know what I'm talking about all day, but no information transfer would occur.
What was he removed for?
Removed?
Removed from the board and later from his, that's the bottom of the page.
Oh, yeah. I don't know, man. He's a little eccentric.
What's got the background of his picture there?
I don't know. It looks like a little trike of some type. He wrote this book, Bicycling Science, and he would ride his recumbent bike to school every day. He tells a story of once he was lassoed. So I could put a little story on there about he was lassoed once by a guy in a pickup truck and dragged down Mass Ave off his freaking bike. Yeah. Well, I'm done anyway. So when we come back, though, let's talk about our own EPA P3 proposal in this sort of Nash game theory context. And I think we should come up with a scenario where everybody wins, right? No losers.